Hey everybody, we're live and in stereo. So in the last class, we talked about Equilibria and we talked about how dynamic equilibrium is reached, and we recapped O-level and IGCSE effectively. We did not do anything new. We just shed more clarity on the dynamic equilibrium and how it's defined and why it's defined like that and all of the good stuff, right? The concentration of reactants and products is no longer changing, but that does not mean that they're equal to each other. It's an isolated system. We did a lot of examples for dynamic equilibrium to solidify the concepts that we had learned, the shaky concepts that we had learned from O-levels and IGCSE, right? Now today what we are going to do is I left you all with a question, which was, in fact, when I said, hey, you have nitrogen reacting with hydrogen, right? And it's a reversible reaction, which means the reaction can go in both directions, right? And you have 2 nitrogens on the left, 2 on the right, therefore 6 hydrogens on the right. So I put a 3 here, and this is a balanced equation, right? So if you have this equation right here, I said we all know that it's a reversible reaction because the reaction can go in both directions, right? And we all know that after a certain point, dynamic equilibrium is reached, which means that after a certain point, the speed at which nitrogen and hydrogen would react together and form ammonia is the same speed at which this ammonia is going to decompose and form nitrogen and hydrogen again. So the concentration of reactants and products are no longer changing. Please, that does not mean they're equal to each other, but they are no longer changing, right? Because the rate at which these products form is the same rate at which these reactants form again. Now, a lot of teachers just start making you guys rote learn the idea of equilibrium constants, but obviously we need to start to be easily transitioned into it, and the transition is very simple. What we wanted to understand was the idea that, hey, after a certain point, we know that a dynamic equilibrium is going to be reached. The rate of forward reaction is going to be equal to the rate of reverse reaction. The concentration of reactants and products will be constant. It will no longer be changing. That doesn't mean they're equal to each other, but they'll be constant, which means they won't be changing anymore. If you have 100 of these and 300 of these and 200 of these, it'll remain that after a certain point, right? Now, the question that we all needed to ask ourselves was that this certain point which is reached, which we call dynamic equilibrium, what is the composition when dynamic equilibrium is reached? What is the composition of this entire mixture when dynamic equilibrium is reached? What I mean by this is, hey, we know that irreversible reactions, they go into 100% completion, right? But reversible reactions, they don't go into 100% completion because dynamic equilibrium is reached. That's actually a problem. Dynamic equilibrium is a problem. Because this dynamic equilibrium state is reached, the reaction never really goes into 100% completion. And we want to figure out at what point is dynamic equilibrium reached. How far has the reaction progressed? Has it progressed 70%? Has it made 70% ammonia, 80% ammonia, 90% ammonia, 60% ammonia? What percentage of products had actually formed before dynamic equilibrium was reached, right? I'm also a Gen Z geek, right? So before, I'm not like, don't associate me with Gen Z, but like B4, right? That's how you guys write it, B4. So how much had the reaction progressed before this state of dynamic equilibrium has actually reached, right? In O-levels and IGCSE, we were never really quantifying this stuff, right? We never really quantified it. We learned about it, but qualitatively. We never really talked about numbers, did we? We never really did, right? We were always just talking about, hey, dynamic equilibrium is reached, dynamic equilibrium is reached. But now in AS level, we want to figure out, hey, how far has the reaction proceeded before reaching this balanced state, before reaching this dynamic equilibrium? And we wanted to quantify this, right? And we asked ourselves, can this be quantified? Can this be quantified? Can we figure out how is the percentage of products that have been made? Does that outweigh the percentage of reactants that you have at dynamic equilibrium? Or does the equilibrium lie more towards the left at dynamic equilibrium, right? Does it lie more towards the left? Which means if dynamic equilibrium is reached, do you have more reactants, more percentage of reactants at dynamic equilibrium, or is it heavier on the product side? Do you have more products at dynamic equilibrium? We wanted to quantify this. Sir, please tell me, how can we quantify this? For that, we came up with something known as the equilibrium constants, right? And the equilibrium constant that we are going to study today is equilibrium constant K, and we write a C in the subscript, because equilibrium constant is denoted by K, right? And the subscript denotes which equilibrium constant we are talking about. So it's the equilibrium constant for concentration. And when we talk about the equilibrium constant, we actually talk about the ratio of products to reactants at dynamic equilibrium, right? At equilibrium. So if equilibrium is reached, what's the ratio of products to reactants? Because that's what we wanted to see. Quantitatively, we wanted to figure out, is this part heavier than this at dynamic equilibrium, or is this part heavier than this at dynamic equilibrium, or are they both equal to each other at dynamic equilibrium? For that, we just calculated the ratio between products and reactants, and we called it equilibrium constant. And this entire idea is projected by something known as the equilibrium law. Right? We don't need to go into details for it, but what we really need to understand is how to calculate this ratio. Now, how do we actually calculate this ratio? I'll write the equation again for you, right? So it's nitrogen plus 3 hydrogen giving me NH3, right? Now we needed to calculate, sir, can we quantify this? Can we quantify this? And equilibrium law said, yes, you can quantify this. We said, sir, how can we quantify this? Equilibrium law said, before you give students this example, give them a general idea of it. And I said, sir, what's the general idea? They said, hey, generally just write an equation. For example, MA plus, these are reactants. M is the coefficient of this reactant, right? So MA plus NB, let's suppose. And this gives me, PC plus QD. These, what I've written here, the smaller alphabets, they are basically my coefficients, right? So equilibrium law said that tells students that if you were to calculate the concentration, the equilibrium constant for concentration, what do? What you do is you actually take, what is it? It's a ratio of products to reactants, not reactants to products. It's products to reactants. So he said, hey, because you're talking about concentration, take the concentration of products, right, at equilibrium, and take the concentration of reactants at equilibrium, and voila, you can quantify it. That's how easy it is. So let's take the concentration of products. Let's call, and we denote concentration with these two brackets right here. This is, when we put these square brackets, we literally mean concentration, right? So I'm going to write here the concentration of C at equilibrium, the concentration of D at equilibrium, and I just calculate a ratio. So concentration of D at equilibrium, concentration of C at equilibrium, concentration of A at equilibrium, concentration of B at equilibrium, right? And because it's at equilibrium, we generally can also write this EQM, because this is the concentration of A and B at equilibrium, the concentration of C and D at equilibrium. And this is what we want to figure out. This formula is nothing out of the blue. It's literally a ratio between products. It's a ratio of products to reactants. And that's what we want to figure out, that at dynamic equilibrium, is this side heavier or is this side heavier? Is product side more heavy or is reactant side more heavy? And we said we can literally find it through basic elementary school math. You have product side and you divide it by the reactant side, right? And so if the Kc value is large, what does that indicate to you? If the Kc value is large, what would that indicate to you? If this value is large, that means the numerator is larger, right? If you get a bigger value from this, the numerator is larger. And if the numerator is larger, that means the product side are heavier, which means you have the equilibrium lies towards the product side. That's how easy it is, literally. And if this is small, if the value of Kc is small, maybe in points, 0.011, whatever, right? If it's small, that means that the denominator is heavier, and the denominator is the concentration of reactants at equilibrium, right? And that's heavier. So if that's heavier, small means that reactants at equilibrium are heavier, and therefore the equilibrium lies towards the reactant side. But equilibrium law said, hey, please don't omit something from it. I said, what? I said, what do you want me to omit? I have not omitted anything. Oh, no. Equilibrium law said, hey, don't omit these coefficients, right? Because these coefficients also play a role in their concentration. And I said, so what should I do to their coefficients? Equilibrium law said, place it in the superscript. They are effectively the powers for it. So it's basically the concentration of C to the power of P, the concentration of D to the power of Q, the concentration of A to the power of M, the concentration of B to the power of N, at equilibrium. So this concentration is at equilibrium. This concentration is at equilibrium. This concentration is at equilibrium, and voila, this is how the equilibrium constant was developed. So it's not a jumbo mumbo formula that you are taught. It's basically logic, because I wanted to quantify the idea of if you have if you have products which are more heavy at equilibrium or reactants more heavy. I said just take the ratio between the two, raised to the power their moles, right? Raised to their molar powers. So I said, okay, let's do that. So at equilibrium, the concentration of this to the power. Why am I taking concentration? Because it's Kc. There are other Ks as well, which you learn in A2, but you're going to learn 2 Ks in AS level, right? So first we are learning Kc, the concentration equilibrium constant, right? And so this is C at equilibrium, the concentration of C raised to the power P at equilibrium, obviously, the concentration of D at equilibrium raised to the power Q, and all of that good stuff. And that's the basic idea of equilibrium constant. So if equilibrium constant is large, if it's large, that means the product side are heavier, which means the equilibrium lies to the products, right, on the product side. And if the Kc value is smaller, that means what? That effectively means that the denominator is heavier, which means what? If the denominator is heavier, I'm getting a call from my mom's. Moms, I'm in class, so I'll call you in a while. Okay. So if the Kc is smaller, that means the equilibrium lies to the reactant side, isn't that? Because the Kc value would be smaller only if this denominator is heavier, and in the denominator we have R. In the denominator we have R reactants. How good is that? How beautiful is this? This is how it was done. Now scientists said, hey, Suleiman Khan, please cut us some slack. I said, what slack? They said, cut us some slack. I said, what slack? They said, stop writing this EQM, 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 EQM all over again, because we know that this is the concentration of C at equilibrium, D at equilibrium, A at equilibrium, B at equilibrium, because we already know that dynamic equilibrium, we want to figure out at equilibrium which side is heavier. So these are already at equilibrium. No need to write it. I said, hey, if I did not write it at the start, students would forget that these are the concentrations at equilibrium. They said, okay, now you've told the students that these are the concentrations at equilibrium. Now omit the EQM from it. We don't like it. It's cluttery. I said, okay. That's the idea of equilibrium constant, right? So this Kc is the concentration of product C, product D at equilibrium. We just don't write this stuff. Maza aa raha hai? Easy. Easy, right? Very easy, very squeezy, lemon squeezy, right? And let me show you guys some photos. And yeah, give me a moment. So I want you guys to focus here. See, this is the general way of writing this. See, he says, note that the products are on the top of the expression. We all know that. That's why we say if Kc is larger, that means the product side is heavier, right? And K is the symbol for equilibrium constant. C is basically the idea. We write C here because we're using the idea of concentration, and the concentration idea is represented by the square brackets. See, these square brackets indicate that concentration are in mole per dm cube at equilibrium. And see, it at equilibrium. Now you know that these are the concentrations at equilibrium. Very important, right? And if there's more than one substance, they are just multiplied here. Like if you have C product, D product, if E product is here, E would be multiplied here to the raised to the power of its coefficient. If A, B, if you had F reactant here, F would also be multiplied here. That's pretty simple. And the powers of the coefficients are the equations for the reaction. That's one idea, are the coefficients of the equations, right? Now this, see, we already looked at this. If Kc is very small, that means what? That the denominator is small. And if the denominator is small, that means the reactants are heavier. The equilibrium lies towards the reactants end, right? So the equilibrium lies to the left, favoring the reactants. That's if the Kc is small. And if the Kc is very large, about 10 raised to the power 3 or larger than this, that means the equilibrium lies to the right, favoring products, right? And this is like a summary for it. See, if Kc is very small, that means what? That the reactant side literally outweigh the product side, right? They're so heavy that the answer is 0.00000 something like that, which means this is very heavy compared to the products, which means the reaction hardly goes. If it's 1, that means the reactants and products are literally equal at equilibrium. They're both equal at equilibrium. If it's like 100 or larger, very, 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 very large, like if Kc is very, very, very large, that means what? That the reaction virtually goes into completion. Almost, it doesn't reach 100% because it's reversible, but almost there, right? And I'll talk about more theory later on, but first I want to give you guys one more idea before we move on to calculation. One more idea. tell me something about this equation. If I'm saying hydrogen reacts with iodine, forms HI, and I said, hey, hydrogen reacts with chlorine and forms HCl, right? And this is the idea right here. 2HI form, 2HCl form. The Kc for this is, let's suppose, 2. The Kc for this, let's suppose, is 1079, right? Or 1018, whatever it is in reality. What does this indicate about the reaction? These questions can be tested in your exams, because nowadays I am seeing Cambridge is moving towards a more conceptual approach, and these are all part of your syllabus. What is it telling me about these two reactions? How are they different from each other? What does this higher Kc indicate? The higher Kc indicates that the equilibrium, the position of the equilibrium lies towards the right. It has, at dynamic equilibrium, you have more HCl, right? And here Kc is 2. It lies more towards the left. And from this you could even deduce things about Hi and HCl, which is what? You can deduce things about Hi and HCl that HCl is more stable. It is more stable, compared to Hi. This is less stable. Why? Why is HCl more stable? Because once it forms, there's a less likely chance for it to go back. That's why Kc is 1018. 1018 means it lies more towards the product end, which means that once this bond forms, there's it's highly unlikely for it to go back. But once this bond forms, the Kc is 2, which means the moment this bond forms, goes back. So tells me about its stability even. How beautiful is that, right? The reaction between hydrogen and chlorine has almost gone into completion to produce hydrogen chloride. I can even say that, This actually indicates, these higher Kc value indicates the stability as well, that hydrogen chloride is more stable at a specific temperature compared to hydrogen iodide. Let's suppose both of these temperatures are like 277 degrees Celsius. Both are at 277, right? So at a particular temperature, at the same temperature, this is more stable than this. So even you could learn about the stability by looking at Kc values. How easy is this? Now, I'm not going to bore you all with more theory. I think this is more than enough for your entire course, but we're going to learn more theory towards the end. Now, I just want to quickly jump into calculations, and this is how it should be taught, right? And before I jump into calculations, let me tell you one more fact about Kc. One more fact about Kc. And this will help us transition into calculations. That fact about equilibrium constant, not just Kc, any equilibrium constant, is that these equilibrium constant only changes with temperatures. Right? Nothing else. Only temperature can change this. Why, you may ask? Only temperature can change the value of Kc. That's it. Now you may ask why. That's theory. And it's, frankly speaking, it's not part of your course. The why is not part of your course. But I will tell you the why towards the end, because if I start talking about the why, you'll just get confused and mumbled. But for now, let's understand the idea that these equilibrium constant can only change with temperatures. Right? And other than that, the value of Kc will always be constant. If you change the concentration, if you change the pressure, if you change whatever other condition you change, this Kc will always be constant. It only changes with temperature. And we're going to look into the why at the end for it, because it's a lot of theory, massive theory, and the why is not part of your course even, frankly speaking. Right? So Kc would only change with temperature. It doesn't change with anything else. Now you may ask me why, the chemistry why for it. I'll tell you, I'm not going to tell you the why. I'll tell you that I'm not going to tell you the why. Then, sir, how did we know? How did we know? If you're not going to tell us the chemistry why for it, the theoretical why for it, how did we know that Kc will only change with temperature and it won't change? For example, if I change concentration, Kc is not going to change, right? I said through experimental data. We performed experiments, and let's perform certain experiments, right? So I'll give you the first one by one. Let's talk about it. I said Kc is only affected by temperature, and you said, sir, why is it not? How is it not affected by concentration? I said it's not. Sir, how do you know? Through an experiment. Sir, which experiment? Let me tell you. For example, N2 reacts with 3 hydrogen gas and gives me, let me prove it to you. Reacts with 3 moles of hydrogen gas and gives me 2 NH3. Can you write the Kc equation for it? It's just a ratio of products to reactants, isn't it? Raised to their coefficients, right? So what's the Kc equation for it? The Kc equation for it is, these are my products, raised to the concentration of products raised to their coefficient, divided by the concentration of reactants raised to their coefficients, right? When nothing is written, it's 1, right? So let's do that. NH3 Concentrate, and remember, these are the concentration at equilibrium, raised to the power 2, and this is N2 raised to the power 1. I'm not going to even write this, and this is H2 raised to the power 3, right? This is the Kc equation for it, right? The equation. And now let's perform certain experiments. And when I performed an experiment, I performed 3 experiments. Frankly speaking, I performed 3 experiments. So which 3 experiments did you perform? I'll tell you. I performed 3 experiments with 3 different concentrations. So show it to us. We don't believe you. I'll show it to you. Just wait a moment. Wait a moment. Hold up. Sir, I found the picture, and this is the experiment which I performed, right? And what I did was, in all these 3 experiments, I varied the concentration of nitrogen and hydrogen, and I played around with their concentration, and at the end, these were the concentrations at, please tell me, what are these concentrations at? See, in experiment 1, you had nitrogen's concentration as this, hydrogen's at this, NH3 as this. Then in experiment 2, you had nitrogen, this concentration, hydrogen. What is this concentration at? Is it at the start or is it at the end at equilibrium? Remember, Kc values are all at equilibrium. That's the idea for it. We want to figure out which side is heavier at equilibrium. So all of these concentration values are at equilibrium. So these are at equilibrium, at equilibrium, at equilibrium, and therefore we can use this. Let's start with experiment 1. So Kc equals NH3 squared divided by N2 and H2 cube, right? So NH3, what's the concentration of NH3 at equilibrium? It's 0. I'm doing this for experiment 1, just proving it to you. So it's 0.157 squared, right, divided by nitrogen's concentration. It's 0.922 raised to the power of 1, which is nothing, and hydrogen's concentration is 0.763 raised to the power 3. Can you guys find this? Please calculate this for equation 1. I'm going to start with equation 2. Somebody calculate it and tell me the answer. Equation 2 is this divided by, again, the same idea, just the values change because I've used different concentrations. Let's see if it changes with concentration. Right? Let's see. And so this would be, for experiment 2, the moles of NH3, the concentration of NH3 is 0.203 squared divided by the concentration of N2 is 0.399 for experiment 2, and for hydrogen it's 1.197 raised to the power 3. Done. Calculate this, please. And then blue is the same idea. Kc equals, always write the expression for it first, because you're just starting out. Don't do things directly, please. Right? What do we get? This is 1.82 at equilibrium. These are all concentrations at equilibrium, please. This is nitrogen is 2.59 and this is 2.77. 2.59 and 2.77 raised to the power 3. Can you guys calculate all of these values? Yes. Fun fact, they're all the same values. All the same values, no difference. This is 0.0602, thank you. This would also, don't go beyond 3 sig fig, please. This is also 0.0602, thank you. This is also 0.0602. And this is the proof for it. So the Kc values, they do not change. They do not change. I repeat, they do not change with a change in concentration. See, because I changed the concentration, and at equilibrium, you had this concentration, this and this. They're all at equilibrium. The value is the same. Fun fact. The question is, what's the unit for Kc? What are the units for Kc, sir? Right? What are the units for Kc? That's the question. Unknown, I'll try to upload it onto YouTube. Happy? Achha, what are the units for Kc? And it's very important to understand this. Dekhiye, I'm going to teach you guys one method, and that's it. You will forever, ever be grateful for this technique. And it's very simple. It's very simple. See, I know that I have NH3 squared, and I have nitrogen and hydrogen, right? And this is to the cube. What would be the units for it? Right? Now, a lot of teachers teach it in different manners. Some teach it in the way I'll be teaching it right now. What is it? It's very basic. It's very simple. See, concentration. These are all concentrations, aren't they? What's the unit for concentration? These brackets are telling me that these are all concentration. What's the unit for concentration? It's what? Mole per dm cube, right? I can add mole per dm cube raised to the power 2 divided by mole per dm cube raised to the power of 1 multiplied by mole per dm cube raised to the power 3, and this becomes hectic, right? And then you start to solve it, and this becomes hectic. Right? This is how it's normally taught. It becomes hectic. I know that mole per dm cube, I'm just going to assign this a value. And the fun bit is that mole per dm cube can also be assigned this m value. You can also assign it any value. It's just math. You can call it A, you can call it Suleiman, you can call it S, B, D, E, F, whatever you want to call it. But normally speaking, when concentration is in mole per dm cube, we call it 1 molar, don't we? M, this capital M. So can I not say that Kc equals m square, capital M square divided by m raised to the power 4, right? And then you just literally calculate it. See, this goes up there, m squared, and this cuts this. You get Kc equals 1 over m squared, right? And if you want to write this at the top right here, you could say Kc equals m minus 2. Isn't that true? Literally. 4, if this is in the divide sign, you could shift it upwards, and then this will be m minus 2. It's just basic grade 6 level math. And what is m? M is effectively mole per dm cube, isn't it? So it's mole per dm cube raised to the power minus 2. So what do you get? Basic math, guys. What do you get? Mole minus 2. And minus 2 times minus 3 is plus 6. So dm 6. This is how you calculate the units. And that's basic. Pretty basic stuff. Very simple. Right? Because you know, when two things are multiplying, this power applies on this and this power applies on this as well. Two things are multiplying with each other. This minus 2 would multiply, this minus 2 would come on top of this, and this minus 2 would multiply with minus 3 right here as well. So minus 2 times minus 3, minus plus. This is the unit for it, right? I'll just give you a quick example. Let's suppose Kc equals x raised to the power 4, y raised to the power, 2, divided by, g raised to the power maybe 3 and e raised to the power 2, let's suppose. What's the units for Kc? And this is such a pathetic question asked in the exam. These are free marks, and if I were the examiner, I'd never test this because these are just free marks. Easy. What's the units? Sir, Kc equals, I'll just call this concentration as m, right? So I'm calculating units now. M to the power of 4 multiplied by m to the power of 2 divided by m to the power of 3 multiplied by m to the power of 2 right here. Done. And so you have 5 m's here and you have 6 m's here. So 1 m is going to be left behind, and that 1 m is what? M represents mole per dm cube. That's it. Khatam. Khalas. That's literally how you calculate units. Right? I'll give you another example. Kc equals x raised to the power 3 divided by y raised to the power, or maybe divided by y raised to the power 1 and e raised to the power, you don't write 1 effectively, but here e raised to the power 4, right? So what do you get? Kc equals m, because concentration is denoted by molar, right? This is mole per dm cube. So m to the power of 3 divided by m to the power of 1 plus 4, 5. You have 5 m's here. So Kc is equal to 1 over m2, right? And this goes up. Right? When it goes up, what is it? It's m minus 2. And then you just open m up. What happens when you open up m up? It's mole per dm cube, and then it's raised to the power minus 2. So again, sorry for the saming. I think it's literally the same thing repeating, but it's mole minus 2 now, and minus 2 times minus 3, it's dm 6. You don't have to do all the jumbo mumbo like this, please. Make your life easy. You'll have to say mole square, dm minus 6, by mole. It'll make your life hell. Right? Easy. And so we've understood through this particular example, we've understood something similar, just like indices. Absolutely. I love this. Okay. Now, if we look at the units for it, you can even tell me it's mole square divided by mole to the power of 4. So it'll be, it's m squared, not mole. It's m square divided by m to the power of 4. 1 plus 3 is 4, right? And then it'll be m minus 2. And m minus 2 is what? M minus 2 is what? This will be the unit for all of them. M minus 2 is what? Mole per dm cube minus 2. So the units for them, all of them, would be mole minus 2 dm 6. Right? Because mole to the power of minus 2 is mole minus 2. dm minus 3 to the power of minus 3 multiplied by minus 2. Minus 2 times minus 3 is plus 6, isn't it? So then here it's also the same. All. It's mole minus 2 dm 6. Mole minus 2 dm 6. And you notice that, hey, Kc values are literally not affected by the change in concentration. Not affected. The whys we learn later on. The why is later on. I don't want to bore you guys with theories. Now, theories to the end. And frankly speaking, the whys are not part of your course. I'm saying this again and again. Right? Rama, it's basic math, please. It's just basic math. What do you do when two substances are multiplying and there's a power? Please, I watch the recording later on. Mole to the power, mole, when two things are multiplying, this minus 2 will come at the power here, and this minus 2 would multiply here as well. It's math. It's basic math, man. I don't know how to explain the math to you. It's when two substances, for example, I say 2 times 2 raised to the power of 2. What happens? This 2 would be squared here, multiplied by 2 squared here. This is a simple indices rule, indices and surds. So it's basic elementary school math, kiddo. ठीक है? मैथ आप देखिएगा, रिकॉर्डिंग दोबारा देख लीजिएगा, समझ आ जाएगी. You'll understand it, inshallah. ठीक है? Now, this idea that I've started, sir, why are you multiplying by mole per dm cube? Rama, because these are concentrations. Concentrations, what's the unit for concentration? It's mole per dm cube, right here. These are all mole per dm cube, mole per dm cube. I'm not multiplying by mole per dm cube. These are concentrations. That's what I said. It's Kc. C is the equilibrium constant for concentrations, kiddo. Okay? I hope it makes sense, right? Now, this idea of Kc being constant at, even if you change the concentration, this helps us out with a couple of relationships. And I'll teach you those relationships. Let's talk about the relationship, right? So the first relationship, let's derive it together. Because if you derive these relationships, it'll stick to your brains forever and ever. You'll never have to rote learn them. Can you guys calculate? I'll just use experiment 1. I'll just use the experiment 1 data, which is 0.922, 0.763. I'll write it 0.922, 0.763, and what else? 0.157. 0.157. Can you guys calculate the Kc for this, please? Can you guys calculate the Kc for this? Right? How do you do this? Sir, products at the top, right? So products, they've just standardized it, right? So NH3 to the square, raised to the coefficients, and 2. Please, these are the concentrations at equilibrium, right? H2, and the reason why I'm stressing so much on this, you'll understand in the next couple of classes. Okay, now, what's the Kc for it? It's again 0.157 raised to the power square, raised to the power 2 effectively. Nitrogen is 0.922 raised to the power 1, and that's why I'm not writing anything. 0.763 raised to the power 3, right? So what do we get, sir? What do we get? We get 0.0602. Isn't that true? That's what we get. And Raima, how do you calculate the units for it? Let's do it. See? This is a representation. These brackets represent concentration. And concentration in what? In mole per dm cube. Right? This is what they represent. So it's effectively mole per dm cube squared divided by mole per dm cube. These are concentrations, Raima. Concentrations are in mole per dm cube. And this is mole per dm cube raised to the power 3. These are the units for it, but I'm not doing it like this. I'm calling this mole per dm cube as m. So it's m squared divided by m into m raised to the power 3, right? So it's effectively what? You have 4 m's and 2 m on the top. So it's m squared divided by m4, right? And this is effectively equal to what? M minus 2, right? This 4 goes up and you get m minus 2. And what's m minus 2? What was m? Then, if you want the proper math for it, let mole per dm cube equal to m or x or whatever you want to call it. Okay? So this is mole per dm cube raised to the power minus 2. Right? And so what you get? What are the units? Mole minus 2 dm 6. This comes at the top here and this multiplies with this. Right? Basic math. Now, this is what we get. Can you guys calculate the Kc? Can you guys calculate the Kc for this reaction? NH3 twice going into N2 plus 3H2. Remember, now I've reversed the reaction. So these are my products, aren't they? Can you guys calculate the Kc for it? Kc is equal to products. Remember, these are always, the products come at the top. Right? That's how we've standardized it. When we say the larger number means the equilibrium lies more towards the products, and that's how we've standardized it. Right? They could have, if they wanted, they could have put the reactants at the top, but they didn't. And this is NH3 squared. Right? True? Products right here Concentration of product at equilibrium raised to its coefficient. Concentration of hydrogen at equilibrium raised to its coefficient, which is 3. Concentration of NH3 at equilibrium raised to its coefficient. What do you get, sir? N2, these are the values, right? N2 is 0.99, 0.922 multiplied by what? H2. H2 is what? 0.763 raised to the power 3 divided by NH3. N is what? NH3 is 0.157, sorry. And raised to the power 2. What do you get, sir? Anybody? I got it? Awesome. I'm glad, kiddo. What do you get? 16.62 or 16.61. 16.6162, whatever, right? And what's the units for it? What's the unit for it? See, now it's what? You have M4 at the top and you have M2 at the bottom. So this 2 cuts out with this 4, you get M2, right? And M2 means what? Mole per dm cube. Mole per dm cube ka square. I'll write it here, wait. Mole per dm cube ka squared. Right? That's what M represents. I've said, hey, let M be mole per dm cube. So if I square this, I'll get mole squared and dm minus 6. Why minus 6? 2 times minus 3 is minus 6. Simple math, right? My question to you guys is, can you guys, and what was the unit here? The unit here was mole minus 2 dm 6, right? First thing I want you guys to notice is something very beautiful. If you check these two values out, this was the unit for the forward reaction. And if I reversed the reaction, the moment I reversed the reaction, what happened to the units of Kc? They flipped. So I can say that if you want the Kc for the reverse, if you want the units of Kc for the reverse reaction, it'll be flip of this. It's like 1 divided by mole squared and dm6. The moment you did a reverse reaction, you said, hey, flip this out. When you flip it, it's like 1 divided by mole minus 2 dm6. And when you solve this, you get mole squared dm minus 6. You take this up, mole becomes squared and dm is minus 6. So I noticed that there's a relationship, a very beautiful relationship per se. What's that relationship? That relationship is, if you want to find the units for Kc for the reverse reaction, if the forward reactions unit are this much, for the reverse reaction, it'll be 1 over units of forward reaction. Wouldn't it be, right? 1 over. I've 1 over this, right? My question to you guys is, can you guys do me a favor and do 1 divided by 0.0602? Can you guys flip this as well? Can you guys do, if this is the Kc for the forward reaction, what is the Kc for the reverse reaction? Can you flip this as well? 1 divided by 0.062. What is that? Yeah, you get the same answer, don't you? You get 16.61 or 16.62, the same answer. And that's the first relationship. That, hey, if you have Kc for the forward reaction and you want to figure out the Kc for the reverse reaction, it's literally inverse of it. That's it. Or if you have the Kc of the reverse reaction and you want to figure out the Kc of the forward reaction, it's literally inverse of it. That's the first relationship. And the units are also inverse. I've literally mathematically proven it to you. Instead of giving you guys rote learns, I've mathematically proven it to you. It's so basic. Such a basic idea. See, you just flip it. The units flip, the Kc values flip. Right? So the everyone chat is disabled. So they become inversed. Absolutely, Aisha. How fun is that? Now, where do we use this? Where do we use this? I'll tell you where we use it. In the exams. When the examiner says, hey, a reaction is carried out, let's suppose, at 700 Kelvin temperature. And the Kc for that reaction is, let's suppose, 0.0602, right? And I say, hey, the reaction is N2 plus 3H2 gives me NH3, right? Can you guys tell me, what is the Kc for the reverse reaction? So if you write the reaction reverse, then this will come at the top, this will come at the bottom, right? Then the Kc equation would look something like this: N2 H2. Would you do the entire calculation all over again, like you're taught, or would you use a shortcut now? You would say, hey, for the reverse reaction, it'll just be flip of the forward, right? So I can just flip the Kc value, which is 1 over 0.0602. What do we get, sir? 16.11, 16.1, 16.11, whatever we get, right? And the units would also be flipped. So if this was whatever units these were, it'll be 1 over those units, and you'll get this value, right? Pretty basic, pretty simple, isn't it? That's the first relationship. There's also one more idea that you could use this first relationship with, and that idea is very simple. For example, I say, hey, can you guys tell me the concentration of NH3 at equilibrium if the Kc for the reverse reaction, this I'm putting a dash here to indicate it's a reverse reaction. So if the Kc of the reverse reaction is 16.11 and the Kc for the forward reaction is 0.0602, right? I can calculate the Kc for the forward reaction. 1 over this would give me the Kc for the forward reaction, right? And the concentration of nitrogen is like 0.922, and the concentration of hydrogen is like 0.763, right? Can you guys calculate the concentration of NH3 using Kc values? Absolutely we can. Now it's time for reverse working. See, Kc equals and Kc prime equals, which is the reverse reaction. Please understand that if this is the forward reaction, right? And I want to use the forward reactions Kc, what should be my equation look like? What should my expression look like? Right? The expression should look like this. NH3, the product should come at the top. Concentration of NH3 squared divided by concentration of N2 into concentration of H2 at equilibrium raised to the power 3. But in this case, if I were to use this expression right here, the Kc value that I would plug in here is what? Is it 16.11 or is it 0.0602? Which value should I plug in? It should be 0.0602 because that's the Kc for the forward reaction. That's the value you need to plug in, and it's pretty basic math. You can calculate, you can very easily, I hope I don't have to do it. You can call this x, I don't know, x squared, and this N2 is there 0.922, H2 is there 0.763. You multiply all of this, you multiply it there, and then you take the under root, right? And please, those of you who are math geeks, you might think, sir, under root gives us plus and minus both values. The answer to your question is, it gives you plus and minus both values, absolutely, but concentration can never be negative, so it's the positive value that you take. Easy peasy. Asan, right? So I hope you guys can calculate it. But if you want to use the Kc for the reverse reaction, then you'll have to flip the expression as well. These are the mistakes that all students tend to make, all students. So now the expression would look something like this. If the Kc of reverse reaction, if I were to plug in 16.11 here, that's the Kc of the reverse reaction, then I'll have to write the reverse reaction, which is N2 plus 3H2. Makes sense? So this would then, the expression would then be N2, and this is H2 raised to the power 3 divided by the reactant side, which is NH3, and these are all concentrations at equilibrium. And whichever method you use, you're going to get the same answer for the concentration of ammonia, and you can try it out at homes. Right? Come on, I hope you guys can solve this simple mathematical equation, right? Easy. Okay, this was the first relationship that we studied, that if you want to figure out the Kc for the reverse reaction and you're given the Kc for the forward reaction, it's just inverse of that. Right? Just flip it out. And if you're given Kc for the reverse reaction and you want the Kc for the forward reaction, just flip it out. You know, if Kc for the reverse reaction is given, just flip it out. That's the first relationship. Right? And this will help you tons in MCQs and exams. Next, for example, I give you the same equation. N2 plus 3H2 gives me NH3. Can you guys tell me the Kc that we had calculated earlier using the values, whatever values we had? N2 was 0.922, H2 was 0.763, and NH3, 2NH3, right? NH3 was 0. The concentration of NH3 at equilibrium was this much. Can you tell me the equilibrium constant that we calculated initially? They'll all be the same, obviously. So it's quite easy after this class. I'm glad, Sarah, I'm glad. Acha. Can you guys tell me the value that we calculated, or should I look? Huh? It's which value? 0.0602. Is this the value? 0.0602. I'm not going to do it all over again and again and again. We've done it like 3 times now. Yeah? So this is the value for it. Now what I want you guys to do is, I want you guys to do something fun. And that something fun is, I want you guys to multiply this entire equation with 2 and then find the Kc value for me, right? So multiply this entire equation with 2. What would you get, sir? You would get 2N2 plus 6H2 gives me what? Gives me 2 times 2 is 4, 4NH3. And the concentrations at equilibrium are the same, 0.922, 0.763, they don't change, 0.157. It's the same experiment. I've just doubled it. Can you guys calculate the Kc value, please? Do it, guys. NH3 at the top, raised to the power 4 divided by N2 squared. It's so fun. These questions are a piece of cake. I'll do very advanced questions with you. Don't worry about it. Don't worry, that's my job. I am built for this. What do we get, sir? NH3 raised to the power 4 is 0.157 raised to the power 4. N2 is 0.922 raised to the power 2 squared, obviously. H2 is 0.763 raised to the power like 6 Sereno. What do you get, sir? Somebody tell me what we get. Yeah. Yeah. Actually, I just wanted the forward, right? This is the forward reaction, so the Kc for the forward is this much. And for the reverse, it will be obviously inverse of it, but we don't care. We're dealing with forward. It's 3.6 into 10 is power minus 3. So it's 0.00362, right? That's effectively 3.6 into 10 raised to the power minus 3. Can you guys do me a favor? Can you guys do me a favor? Can you multiply this entire thing with 2 just like Raima said? Can you guys multiply 0.0? Because you're multiplying the equation with 2, can you guys multiply the Kc with 2 as well? Just like Raima said. Let's see if Raima is right. Let's check it out. It's good. It's good. It's good to, have these assumptions. It's good. Can we check out? You get 0.1204, Raima. Is this matching this? It's not, right? So it must be something else, right, Raima? It must be something else. And when you multiply an equation with coefficients, see, what effect does multiplication have? It's pretty basic math, And I'll tell you what basic math it is. See, when you have coefficients are the superscripts, aren't they? Coefficients are NH3 raised to the power 2. So if this NH3 is double, this power would be doubled. And therefore, if you double an equation, if you multiply this entire equation with 2, these superscript double. And when superscripts double, the power actually doubles, right? So the power is doubling. So can you guys do me one favor and just take the square of this? That's the second relationship. So it's pretty basic math, wasn't it? It's pretty basic math. See, when you write the Kc equation for yourself, the expression for it, what's the expression? The expression has powers right here. These coefficients are effectively the powers for it. So if you double it, it will be squared. If you triple it, it'll be cubed. If you quadruple it, it'll be to the power of 4, wouldn't it? Can you guys give me the value for it? It should effectively be 0.00362. Right? And even the units would also be squared, right? So if the previous units were whatever, what were the previous units for this? The previous units, it was what? If I'm not wrong, it's like mole minus 2 dm6. These were the previous units, right? So now they would also be squared. So now it'll be mole minus 4 dm, and 6 times 2, that's 12. These would now be the units, wouldn't they? And you could check them out. See, you had 4 and you had 8 here. So it's m minus 4. And m minus 4 is what? Mole per dm cube raised to the power 4. And that gives me mole to the power of 4. Sorry, mole raised to the power minus 4. Mole to the power of minus 4 dm. 3 minus 4 times minus 3. It's it's minus 4 times minus 3. It's 12, right? And you could check this out. Yeah. Yeah, no, kiddo, Raima, please, it's basic mathematics. It's indices insert. I hope your math teacher is good. Mole, and if you take 2 multiplied by 2 and square it, please, I'm not here to teach math, kiddo, but it's okay, I'll teach it. If you take 2 into 2 and then square it, what does that give me? 2 into 2 is 4, 4 to the power of 2 is 16. And if you want to put the square on it, this square would individually come here and here. So it'll be 2 squared multiplied by 2 squared. 2 squared is 4, 2 squared is 4, and that's 16. So you didn't take the power of it, you multiply it. It's like 2 times, when nothing is written, it's to the power of 1. So you're multiplying 1 with 2, 1 with 2. Right? It's O-level math, kiddo. Not even O-level. Even if you don't take O-level math, it's basic elementary class math. Come on. It's okay. It's okay. Chalo. I hope you got it now. Okay. Indices, inserts. Acha. And so this is where the next relationship has been derived is if I have Kc value, if I have Kc value for an equation and I multiply the entire equation with 2, I multiply the entire equation with 2 or multiply the entire equation with 3, what would happen if I double the coefficients? What's going to happen? If I double the coefficients, what's going to happen? It's going to have a squared effect. So Kc1, the Kc1 that I had, right? This Kc1 that I had, this stuff would be squared. So the new Kc, which I'll call Kc2, this Kc2 would be equal to Kc1 ka squared. Isn't that? Right? So once you doubled the coefficients, the new Kc would be squared of the old Kc. And this is what we've done. The new Kc value is the square of the old Kc. Isn't that true? How easy. And I'm deriving these equations for you instead of feeding it to you. Right? So the first relationship that we had studied was just relationships, very simple, right? And you could not know these relationships. It's absolutely okay to not know these relationships, then you'll have to solve it. If you want to solve it in the MCQs, good luck with that. So it's the first equation is if you want to find the Kc of the reverse reaction, it's flip of the original Kc. And the second relationship is if you double the coefficients or triple the coefficients, the new coefficient, this is Kc new. The new coefficients, if I double it, if I double the Kc, if I double the coefficients, the new Kc would be squared of the old Kc. I'll write it like this so it's bilkul crystal clear. And if I triple it, the new Kc, Kc2 or Kc new would be equal to the cube of old Kc. Isn't that? If I want to quadruple it, the new Kc would be equal to quadruple of the Kc, right? So you don't have to. And the units would obviously therefore square here, cube here, 4 here, right? That's it. That's the basic idea. So 2 relationships done. Next relationship is what if I half it? What if I half the coefficients? Now, I'm not gonna solve it, derive it. It should be in your brains now. What if I half the coefficients? You need to do the math on your own. Shabash. What if I half the coefficient? If doubling the coefficient had a squared effect, yes, Sarah, you are absolutely right. If I halve the coefficient, the new Kc, which I'm calling Kc2, would be equal to the square root of the old Kc. And if I 1 over 3 the coefficients, 1 over 3, if I 1/3 the coefficients, then it would be new Kc would be 1/3 of the old Kc, right? 1/3. Right here. Under root can also be written like this, right? Kc 1 over 2. Similarly, 1 over 3 can also be written as this. Right? If I, quarter it out, if I quarter the coefficients, this new Kc would be equal to the old Kc, and then tetra, what do we call this? We don't call this under root, right? 1 over 4 is called square root is this, or under root. 1 over 3 is called cube root. This is called tetra root. What is it called? Tetra root? Whatever it is. Yeah, that's how easy it is. And you can do the math. If you want to prove it for yourself, take the same values, half it, and do it with the same things. You can prove it for yourself. I just can't be bothered, right? That's the third relationship. The fourth relationship is also very crucial and very, very much tested. This is effectively the fourth root. It's called the fourth root, not the quadruple root. Okay, not the tetra root. Okay, good stuff. New addition. Sir, how are you a chartered accountant? Even I don't know. Acha, next. We don't study roots, we study percentages and consolidations and whatnot. We are cooked. IFRS 9 is killing us, banks are killing us. Next, enough with my ranting. The last relationship, which is very crucial, rarely tested. Again, these relationships are barely tested, but when it comes in MCQs, they're going to save a hell lot of time for you all. I call this relationship as sequence of reactions relationship. Sir, what do you mean sequence of reactions relationship? I'll tell you. Sir, please scroll up to point 3. I'll take a screenshot. Here you go. Done, Aisha? Easy. Can I move forward? Just 10 more minutes and we are done. 10 more minutes and then we are done. And tomorrow we're going to learn the ice tables. That's my favorite part. Sequence of reactions relationship. Sir, what do you mean by this? For example, I have Kc1, whatever this is, I don't care. It's nitrogen reacting with oxygen to give me NO, right? And then I have Kc2, which is like NO, this particular NO which has formed, this further reacts with O2 to give me NO2. Right? Let's even balance this out. I put a 2 here, right? If I were to, okay, I'll balance it out in a better. I put a 2 here and a 2 here, and that's balanced. But I could have also put a half here, couldn't care less. This is the equation, and this is a 2 here. Thank you. This is reaction 1, and this product is further being used in this particular reaction. So this reaction will have a Kc. This reaction will have a particular Kc, right? Can you write the Kc for the first reaction? Kc1. Can you guys write the Kc for the first reaction? It's NO squared divided by N2 and N2 concentration at equilibrium and O2 concentration at equilibrium. Okay. Can you guys write Kc2? Which is what? Kc2 is NO2 product squared divided by what? Product squared divided by 19. Do it. Product squared divided by NO squared and O2. That's it. Okay, these are the two cases. Now, what I want you guys to do is, I want you guys to add these two equations to each other. So how would you add these two equations to each other? See, nitrogen plus oxygen, you're going to get 1 mole of nitrogen plus 2 moles of oxygen. Sir, why aren't you writing NO? Because NO is here and NO is here. Won't they cancel out? On the left and right, both NO would cancel out. And you're going to end up with 2NO2 at the end, right? What's the Kc for this third reaction? This is what I want to figure out. Now, there are two ways. You might be given values for all of them. You would use these values to calculate the Kc out for the third reaction, right? And what's the formula for it, please? What's the expression for it? Not the formula, the expression for it. It's NO2 squared and then N2 concentration and then it's O2's concentration squared, right? That's the idea. Now, I want you guys to have a look and see what you can do with this Kc1 and Kc2 to actually get Kc3. What can you actually do in a sequencer? Use your brain, use your mathematical skills. See, I've written all the equations for you. You just have to think, right? And you could even think like this. If multiplying the entire equation had a squared effect with 2, obviously. Multiplying the entire equation with 2 had a square effect. If I add the two equations, what effect would it have? Think. See, you could even derive logics. If multiplication had a superscript effect, which is squared, cube, and whatever, if I just add them, addition would have what effect? Multiplication has squared effect, so addition shouldn't have multiplication effect? It should. It should, Sarah. You are right. It should have a multiplying effect. So Kc3 would be equal to, if you want to directly find it, it will be equal to Kc2 into Kc1. Sir, but you haven't proven it to us. I'll prove it to you. Take the expression of Kc2, NO2 squared. Right? I'm writing this right here. Kc2 into Kc1. I'll prove it to you. NO2 squared, right, divided by what? NO squared, O2, right here, multiplied by what? Multiplied, sir, with what? Kc1. This is NO squared divided by N2O2. Concentration of N2, concentration of O2. What happens? NO squared cut out. What do you get, sir? NO2's concentration squared divided by O2 and O2. O2 squared. This is N2's concentration and O2 squared. And what is this? Is this not Kc3? So I know a lot of you might hate me for teaching you guys all of this stuff, but this is important for MCQs. That's the only reason why I taught you guys this idea. Only reason. Sir, I can't see your screen. It's stuck. Aisha, it's not stuck for me. Rejoin. Yeah, just rejoin. Done, guys? So effectively, we've studied 4 relationships, and these relationships are only to be used in complicated questions if you're not given datas, or if you're short on time and you could use it in MCQs. Number one, if you're given a KC and you want to figure out the KC for the reverse reaction, it'll be just a reciprocal, right? It'll just be flip of the first KC. If you double the coefficients of a particular equation, the KC would have, the new KC would actually be squared. The KC new would be equal to the old KC and square that stuff up. Old KC raised to the power of 2. If you double the coefficients, I'll write it here, double and triple it, so then the idea is the same. Triple it, it'll have a cubic effect and whatever, right? But if I half it now, if I half the coefficients, right here, half the coefficients, what's going to happen? It's going to have a under root effect. So the new KC new would be equal to under root of old KC, or you could write it like this. If you are good in math, you could write under root is 1 over 2, isn't it? Cube root is 1 over 3, isn't it? And then the last equation is, if you have a series of reaction and you're adding reactions, you're adding addition of equations, the new KC new would be equal to the product of all the KCs. So KC1's product, KC2 product, KC3 product, and so on and so forth. However many reactions you have in a sequence, they will all the KCs would be multiplied to give you the new KCs. Right? So these are the 4 relationships, very important, help you out a ton in MCQs and whatnot. And I'll show you the summary for it as well. This is the summary, and we are done with today's class. But before I end it, I want to tell you guys something. Before I end the class, let me show you guys a quick summary. Just give me a moment. Sarah Singh, I understood, love it. This is a summary. If you want to write the KC of the reverse reaction, it's literally inverse. 1 over, it's inverse of the first one. Rabia Singh, kindly scroll up. Here you go. Rabia, this is actually the summary written right here in front of you. If you halve the stoichiometric coefficient, it has a square root effect. If you double the stoichiometric coefficient, it has a superscript effect. If it's a sequence of reactions, it's the new KC would be equal to the multiplication of all the other KCs. That's how easy it is. How easy. And I've proven everything to you. Instead of showing you guys this stuff, I've proven it mathematically. Everything, everyone. Sir, tomorrow's class will also be public. Chalo, done toota hua saas. Tomorrow's class will also be public, but it'll be at 9 p.m. because I will get killed by my online batch students. They will kill me. Some of them won't kill me. Sir, kal class na ho. No, Raima, tomorrow. Now, before I end this, I want to tell you guys something. And let me end it with a cliffhanger. It's not so simple, is it? Because the Cambridge examiner is saying, hey, what's the point if I give you the concentration at equilibrium? You've understood the idea. You guys can just quickly tuck and find it. Why would I give you concentration at equilibrium? Am I dumb to give you concentration at equilibrium? Find it, you dumbos. Find concentrations at equilibrium on your own. Find it on your own. You'll have to figure out the concentration at equilibrium. Then I said, Cambridge, what are you going to do, you dumbo? What are you going to do? I will just give you the moles I'm reacting. I'll just give you the moles which are reacting. You go out and figure out concentrations at equilibrium. So all the examples that we did, please understand that these were the concentrations at equilibrium which the examiner will never really give it to you in the exam. It will never be given. If it's like a 0.1 mark question, they'll give you these concentrations at equilibrium because then it'll be a piece of cake. Concentrations at equilibrium, just plug it in the expression and you're good to go. Examiner saying, oh no, you dumbo. Oh no. I will never ever give you these concentrations at equilibrium. Go find it on your own. So what are we going to do for it? We are going to learn a particular method called the ice tables. And I'm so glad that, back in the day when I when I first taught A-levels, I think it was 2020, 2021, when I first taught A-levels, these ice tables were not known to many teachers. Now, alhamdulillah, I'm glad that a lot of teachers now know these ice tables and know good use of it. So I'm glad. But if you have not been taught these ice tables in this particular chapter, you're cooked. Then what are you doing? So inshallah, tomorrow's class you'll learn how to figure out concentrations at equilibrium. Once you have the concentrations at equilibrium, you're good to go. You just use the idea. You write the expression, use the idea, and plug in the values, and you're done. But now we learn how to figure out the concentrations at equilibrium. That's the major step which we'll be learning tomorrow. Yeah. Omar saying, what's your actual age? Omar, you asked me my age and then you left the class, mate. No.